topic of this video will be the synthesis of ketones and aldehydes through reduction of carboxylic acids and their derivatives. Ketones and aldehydes can be synthesized through the reduction of more oxidized compounds, like carboxylic acids, esters, acid chlorides, or nitriles. In these reduction reactions, the carboxylic acids and their derivatives take the form of this: a carbonyl compound with a leaving group attached. Reduction occurs through the addition of hydride or carbon as a nucleophile. In the case of hydride reduction, we get replacement of the leaving group with hydrogen to produce an aldehyde. If the reduction occurs through the addition of carbon as a nucleophile, we see replacement of the leaving group with a carbon, producing a ketone. Both of these processes are reductions because we reduce the number of bonds from carbon to more electronegative atoms. Remember that both the aldehyde and the ketone are easily reduced further to the alcohol, so typically we need a special, less reactive reagent to stop the reduction at the ketone or aldehyde stage. Let's start our discussion with the synthesis of ketones. First, we'll talk about how ketones can be synthesized from carboxylic acids. Treatment of a carboxylic acid with a reducing agent or an organometallic reagent typically leads to deprotonation of the acidic proton, because the reducing reagent or the organometallic reagent act as a base. However, organolithium reagents are reactive enough to reduce the carboxylate salt that is produced upon deprotonation. So typically, we treat the carboxylic acid with a strong base first to deprotonate it, followed by treatment with the organolithium reagent, and finally an acidic workup. This sequence of reagents produces the ketone. In the first step, lithium hydroxide deprotonates the carboxylic acid to produce the lithium carboxylate salt. In the next step, the organolithium reagent is added. The organolithium reagent attacks the carboxylate, producing the dilithium salt. In the acidic workup step, both salts are protonated to produce the hydrate. The hydrate is unstable and rapidly loses water to produce the ketone. It is important to note that only organolithium reagents are reactive enough to add to the acid. This does not work with a Grignard reagent. Finally, sometimes, if the organolithium reagent is cheap, we can skip the first step and just add 2 equivalents of the organolithium reagent. The first equivalent of the organolithium reagent acts like a base to deprotonate the carboxylic acid, and the second equivalent acts as a nucleophile to add to the acid and produce the ketone. Next, we'll consider the synthesis of ketones from nitriles. Remember that a nitrile looks like this, and a nitrile has a dipole that points in the direction of nitrogen. For this reason, a nitrile reacts similarly to a carbonyl compound. The carbon of the nitrile is electrophilic, and therefore will react with nucleophiles such as Grignard reagents, organolithium reagents, and reducing agents. Therefore, if we'd like to convert a nitrile to a ketone, we need to react the nitrile with either a Grignard reagent or an organolithium reagent. In this example, we will use a Grignard reagent, but know that an organolithium reagent will react in exactly the same mechanism with a nitrile to produce a ketone. Reaction of a nitrile with an organolithium reagent or a Grignard, followed by addition of acidic water, will produce the ketone. In the first step of the mechanism, the Grignard or organolithium reagent attacks the carbon of the nitrile to produce the magnesium salt of an imine. This salt is stable to further nucleophilic addition, and therefore no additional reaction will occur until the acidic workup. Upon addition of acid, the salt of the imine is protonated. This produces the imine. The remainder of the mechanism is the hydrolysis of an imine, which is the reverse of a synthetic mechanism we will talk about later in the semester. The imine is protonated to form the iminium ion. Protonation of the nitrogen makes the carbon a good electrophile for attack by water. Next, water deprotonates the hydroxyl group. Next, the amine is protonated. And the carbonyl forms to kick off the amine. Finally, the ketone is deprotonated. To form the final ketone product. Finally, ketones can be synthesized from acid chlorides. Acid chlorides are the most reactive of the carboxylic acid derivatives. Remember that if we react a Grignard or an organolithium reagent with an acid chloride, it produces the alcohol. The addition of one equivalent of Grignard or organolithium reagent produces the ketone. However, the ketone is more electrophilic than the acid chloride, and therefore we can't stop further reaction of the ketone with more of the Grignard or organolithium reagent to produce the tertiary alcohol after an acidic workup. Because the ketone that is formed from the addition of one equivalent of the Grignard or organolithium reagent to the acid chloride is more reactive than the original acid chloride, it reacts with any remaining Grignard or organolithium reagent as soon as it's formed, even if we try to limit this reaction by only adding a single equivalent of the carbon nucleophile. Therefore, we need a less reactive carbon nucleophile to convert an acid chloride to a ketone. In other words, to stop the addition after a single equivalent of the carbon nucleophile has added. The less reactive carbon nucleophile that we can use to carry out this transformation is called lithium dialkyl cuprate, otherwise known as a Gilman reagent. A Gilman reagent has the formula R2CuLi. Gilman reagents are capable of carrying out the acid chloride to ketone conversion. The Gilman reagent is less reactive than a Grignard or an organolithium reagent, and therefore will only react with the acid chloride. We can synthesize a Gilman reagent from an organolithium reagent. Combination of an organolithium reagent with copper iodide produces the Gilman reagent. Next, we will consider how to synthesize aldehydes from carboxylic acid derivatives. First, let's consider the synthesis of aldehydes from nitriles. In the past, we've used lithium aluminum hydride or sodium borohydride for reductions. Sodium borohydride is not reactive enough to react with a nitrile, and lithium aluminum hydride is too reactive. It will reduce the nitrile all the way down to the amine. Therefore, we need an intermediately reactive reducing agent that will stop after one addition of hydride to the nitrile. The reducing reagent that has been developed for this transformation is called diisobutyl aluminum hydride. It is commonly abbreviated as DIBAL-H, or like this. I prefer this second notation because it better construes the structure of this reducing reagent, which looks like this. Unlike other reducing reagents we've looked at, the aluminum is not negatively charged, and it only contains one hydride to donate. Both of these things make it less reactive, so that only a single equivalent of hydride is added to the nitrile. In the first step of this reaction, we add the diisobutyl aluminum hydride to the nitrile. The hydride adds to the carbon of the nitrile to produce the aluminum salt of the imine. In the next step, an acid workup is performed to produce the aldehyde. The mechanism for the second step is the imine hydrolysis mechanism that we looked at previously when converting a nitrile to a ketone. Next, we will consider the synthesis of aldehydes from esters. Just like we saw with nitriles, sodium borohydride is not reactive enough, and lithium aluminum hydride is too reactive. We've already seen that treatment of an ester with lithium aluminum hydride will reduce the ester all the way down to the primary alcohol. Just like nitriles, we need a less reactive reducing agent to stop after one addition of hydride to the ester to produce the aldehyde. And again, we can use diisobutyl aluminum hydride. However, because esters are more reactive than nitriles, we also have to do this reaction at a very low temperature, so that only a single equivalent of hydride is added to the ester. In the first step, the ester is treated with diisobutyl aluminum hydride at minus 78 degrees Celsius. This produces the aluminum salt, which is then hydrolyzed in the acid workup step to produce the aldehyde. Finally, we can produce aldehydes from acid chlorides. Again, reduction of an acid chloride with lithium aluminum hydride produces the primary alcohol. We need a less reactive reducing agent in order to stop after the addition of one equivalent of hydride ion. Because acid chlorides are the most reactive carboxylic acid derivative, we need something even less reactive than the diisobutyl aluminum hydride. What we use in its place is lithium tri-tert-butoxy-aluminum hydride. This compound is also often written like this. The tert butoxides serve to draw electron density away from the aluminum as well as make it bulky. This makes the hydride less nucleophilic and makes it able to stop the addition of hydride to the acid chloride after a single equivalent. Treatment of an acid chloride with lithium tri-tert-butoxy-aluminum hydride produces the aldehyde. The acid chloride can be synthesized from the carboxylic acid using thionyl chloride, just like an alcohol. Finally, let's summarize the different reducing reagents we've discussed. Ketones and aldehydes can be synthesized from carboxylic acids and their derivatives using the following reagents. Ketones can be synthesized from carboxylic acids using the organolithium reagent. There is no way to directly synthesize an aldehyde from a carboxylic acid. Ketones and aldehydes can both be synthesized from nitriles. Ketones can be synthesized by the addition of organolithium reagents or Grignard reagents to nitriles, while aldehydes can be synthesized from nitriles using diisobutyl aluminum hydride, which is a weaker reducing agent than lithium aluminum hydride. Both ketones and aldehydes can be synthesized from acid chlorides. Treatment of an acid chloride with the Gilman reagent produces the ketone. Remember that the Gilman reagent is less reactive than the Grignard or the organolithium reagent, which is why it can react with a more reactive acid chloride to produce a ketone. To convert the acid chloride to an aldehyde, we need lithium tri-tert-butoxy-aluminum hydride, which is an even weaker reducing agent than diisobutyl aluminum hydride. Finally, aldehydes can be synthesized from esters by treatment with diisobutyl aluminum hydride at minus 78 degrees Celsius. Using the diisobutyl aluminum hydride at cold temperatures makes it a weaker reducing agent than if it's used at room temperature, like with a nitrile. There is no way to directly synthesize a ketone from a carboxylic ester.